Hello viewers, we have been discussing the instruction set of microprocessors, particularly that of 8085 microprocessor in detail. Let us pick up the thread from our last lecture. In the last lecture, we have discussed two different classes of instructions like data movement instructions and data manipulation instructions. In this lecture, we shall be discussing program manipulation instructions, status manipulation instructions, and miscellaneous instructions. The program manipulation instructions can be further divided into several types. For example, we have the unconditional jump, conditional jumps. They belong to the jump or they belong to the branch group. Branch group. Then we have these two belong to branch group, subroutine call and return, software interrupts. We shall consider these types of instructions one after the other. Let us first consider the unconditional jump. As I told, the branch group can be broadly divided into two types. One is unconditional and another is conditional. Now, as you have seen, whenever you are executing a program, normally you are executing in consecutive memory locations, and the address is given by the program counter, one after the other. Whenever you finish fetching an execution of an instruction, the program counter is automatically incremented to point to the next instruction. So the program counter supplies the next instruction address in normal instruction execution. But there are situations where the instruction has to come from some other point. In other words, you would like to deviate from the normal instruction execution flow. You would like to execute from some other location. In such cases, you will require this branch group of instructions. The unconditional instruction in case of 8085, it is called jump JMP ADDR. This is the mnemonic for that jump, unconditional jump instruction. Then what it does, it loads the program counter with the value provided by this instruction, byte 3 and byte 2. So byte 3 and byte 2 are provided as part of the instruction in this way. This is the format of the instruction. This is the instruction format 1 1 0 0 0 0 1 1. This is your opcode. Then you have got 2-byte address ADDR provided as part of the instruction, and this byte 3, this is byte 3 and byte 2. As we know, the byte 2 provides the lower order address, and byte 3 is the higher order address in the instruction. So that is being loaded into the program counter, and you may call it immediate addressing, because what you are providing the data in the immediate form as part of the instruction. So how much time it will require to execute? First of all, the instruction fetch will take place, and then these two addresses are to be fetched and it will be loaded into the program counter. That is what the instruction does. So it will require 3 clock cycles, one to fetch this, next to fetch these two, and it will be loaded into the program counter. And number of states required will be obviously 4 plus 3 plus 3, that is 10. Now With the help of this instruction, the programmer can write a program to jump to a particular address without any condition. But there are situations where you have to take decision, and based on that decision you have to execute jump or should not execute jump. Where from these conditions will come? The conditions come from the outcome of instruction execution. We have seen that in the CPU there are some flag bits. For example, you may recall we discussed the register organization of 8085, and here there is one special register where there are 5 flag bits: carry, parity, auxiliary carry, 0 and sign. These flag bits are modified whenever you execute an instruction. Obviously these flag bits will change. For example, whenever there is a carry, because of the execution of add instruction, this flag bit will set to 1. So whenever there is some carry or carry occurs, you would like to jump to some location, or when the result is 0, Z flag bit is 1, then want to jump. We have seen that this auxiliary carry is commonly used to implement that DAA instruction, decimal adjust accumulator, to facilitate BCD mode of addressing. But the other 4, carry, parity, 0 and sign, these 4 can be used as the condition. For example, we can provide it in the form of a code. So this is the code. Or rather you can say this is the condition. Based on this condition, the jump will occur. First one is not 0. Whenever the result of instruction execution is not 0, that means Z flag bit is not set, not 0. The code is 0, 0, 0. Whenever this Z flag bit is set, then Z is 1 and the corresponding code is 0, 0, 1. Whenever the code is, say, no carry means CY flag bit is 0 and the corresponding code is 0, 1, 0. Then carry, when the carry flag bit is set, CY is equal to 1, then the code is 0, 1, 1. Then whenever you have the parity odd, whenever the parity is odd, then parity bit is 0. Your condition, this condition, these 3 bits, the code will be 1, 0, 0. When the parity is even, then P is equal to 1. That means the parity flag bit will be set when the parity of the number is 1, the result that the which is in the accumulator, and whenever the sign S bit is 0, that means positive number, then the code is okay. For P is 1, 1, 1, 0, 1. For parity it is 1, 1, 0. And finally, whenever your result is minus, that is negative, S is equal to 1 and we get 1, 1, 1. So these 3 bits are used as part of the instruction to state which particular condition will decide the jump. For example, the instruction format for conditional branch instruction is like this. You have got 1, 1, then CCC 0, 0, 1, 0, and obviously you will be provided with the address in the same way as the unconditional branch. And here the CCC, depending on which condition you want to use, whether it is not 0 or 0 or no carry or carry, odd parity or even parity, these 3 bits will be accordingly used. That means the code will be decided based on the condition. One thing you must notice here, in case of this unconditional jump, the time required is fixed. The number of cycles is 3 and number of states required is 10, which is not true in conditional in conditional branch instructions. For example, whenever the condition is not satisfied, obviously you will not fetch this address and jump to a new location. You will not perform this operation. On the other hand, when this condition is satisfied, then you will fetch this instruction, fetch these addresses, these 2 bytes, which is the address which will be loaded in the program counter. Then the time required will be different. That's why you see, you will find the number of cycles required is equal to 2 or 3, or number of states required is equal to 7 or 10. That means whenever the condition is not satisfied, you require lesser time to execute this instruction, that is 2 cycles or 7 states. On the other hand, whenever the condition is satisfied, you have to load this address into the program counter. Then you will require 3 clock cycles, 3 machine cycles, and number of states required will be 10. So this is the unconditional and conditional branch instructions. Now, whenever you are writing a program in a modular fashion, obviously you will write main program, you will also write some subroutines, and to facilitate that, there is facility for subroutine call and return instructions. The what it does, the basic code is call ADDR. This is the mnemonic of the instruction. What it does, whenever you perform subroutine call, you have to load the program counter with some new value, and program counter has to be incremented by some value. So program counter, what it does, that stack, you have to load the program counter in new value, but before that, that program counter has to be saved so that you can return to this point. For example, the operation performed by this subroutine call instruction is like this: stack pointer -1, that is the address, which is loaded by program counter high. For example, this is your stack. Let's assume this is your stack. We know that stack is implemented with the help of a stack pointer. Let's assume the stack pointer is pointing to this location. In case of 8085, what it does, that program counter high value, PC high, will be loaded in the next lower instruction, SP-1, as you can see here. Similarly, the stack pointer that PC low is loaded, program counter low, lower order byte, sorry, low, this is your PCL, is loaded in the next lower location, that means SP-2. So after performing this instruction execution, this stack pointer will point to this location where the lower order byte of program counter is stored. And the program counter will be, as I said, program counter will have the value, stack pointer will have the value SP-2, and program counter will be loaded with a new value where you have to, where your subroutine is stored. So byte 3 and byte 2 provided as part of the instruction will be stored there, and because the code for the instruction is 001101. This is the opcode, and you have the address provided as part of the instruction, and this is the address which is loaded into the program counter. Here you see the total time required is quite long. Total number of cycles required will be 5, because you have to perform so many operations. You have to not only fetch these 2 bytes, which is provided as part of the instruction, but you have to load them into the program counter, and before that the program counter has to be loaded into the stack. That's why the total number of cycles required is 5. That means it will perform machine code fetch cycle, followed by 2 read cycle, then followed by 2 write cycle into the stack pointer stack. Those 2 current value, the next address has to be loaded, and then uh, so two machine code instruction fetch cycle followed by two read cycle followed by two write cycle. So total number of cycles will be 5, and total number of states required will be 18 clock cycles. So it takes quite long time to call a subroutine. Just like the conditional branch and unconditional branch, the subroutine call can also be conditional. This particular instruction which we have discussed right now can be called unconditional subroutine call. There are situations where subroutine call will take place based on the condition. So you can use the same condition, and in that case the corresponding the code is so condition C condition followed by address, and we shall be using the same condition codes, that CCC values, as part of the instructions. Here is your CCC, and then edit address. So the same conditions which are used here in case of your unconditional branch, same are used in case of conditional subroutines. So the total cycles required is either 2 or 5. So you see here again the time required is different. When this condition is not satisfied, then the number of machine cycles required is only 2, but when it is satisfied, then you require the same time as the unconditional call, and number of states required will be uh, number of states required again will be varying 9 or 18. So you find there is some difference in execution times in case of conditional subroutine calls. Now the way it happens is like this. Suppose this is the program, and in your program somewhere here you have got this call ADDR. This is the subroutine call instruction. What will happen because of this? First, as we have discussed, this address this address will be loaded into the program counter, and the next address, this address which is immediately following this instruction, will be loaded into the stack. So the jump will take place to the beginning of the subroutine. Suppose this is the beginning of the subroutine, and this is your subroutine, which is also residing in the same memory. Now after you have jumped to a subroutine, suppose this is where the subroutine ends, you want to return back to this point where you that means where your next instruction is stored. So to do that, to facilitate that, you must have a return instruction. Otherwise the situation will be like Abhimanyu of Mahabharata. He was not knowing how to return from Chakravyuha. So you must know an instruction by which you can return from the subroutine call, and for that purpose there is a return instruction. Return instruction is short one. The code is like 11001000. What happens because of this? What it does, whenever this return instruction is executed, the value which is stored in that means at the end of each subroutine you must have a return instruction. That is the last instruction of a subroutine, and outcome of this is the stack which was holding the PCL and PCH values will be loaded into the uh, program counter. That means because of this the program counter will be loaded into the instructions from the stack. Since these two values are there in the stack, they have to be fetched. but you see you don't have to specify the address, because stack pointer is already pointing to these two values. So lower order address, so it will execute some kind of those pop operations, and the program counter will be loaded, and it will require, obviously, although the instruction is of only 1 byte, it will require 3 cycles. First one is machine fetch cycle, and following two are the read cycles from these two from stack, and it will be loaded into the program counter. So total number of states required will be 10. Now, just like the subroutine conditional branch, conditional subroutine call, you can have conditional return as well, like this. 11 CCC 000. Here again, since it is conditional, the execution time will be varying. For example, if the condition is not satisfied, you will require only 1 cycle. If it is satisfied, you will require 3 cycles to return. Then the number of states will be either 6 or 12. So whenever it requires only 1 cycle, as you can see here, the number of states required is 6. So there are some machine cycles where you require 6 clock periods or 6 number of states. Now, whenever you are calling a subroutine, although the program counter is being stored in the stack, apart from program counter, you may be using some registers. Some registers may be holding some useful intermediate data, which you will require after you return from the subroutine. Those registers may get modified if you don't save in the stack. So that to facilitate that, there are several instructions like push register pair. Those register pairs like B, C, D, E, H, L, those register pairs can be stored in the stack by, by using this push instruction, or you can perform push PSW, program status word. Program status word comprises of the accumulator and these PSW register. That means these two registers are stored whenever uh, push this push PSW instruction executed. That means if any registers are being used to hold, if any registers are holding some useful result, then you should use those. I mean, before calling the subroutine, somewhere here you should perform those push operations, push register pair or push PSW. So you must do that, otherwise the information stored there will be lost as you execute the subroutine, because subroutine may be using those same registers and they will be modified. That means whenever you go to the next part of the program, then you may not get the proper values. How will you get back them? You have got complementary matching instructions like push PSW, pop PSW, or pop RP register pair, and also you have some additional instruction like XTHL, which are sometimes useful in the context of stack these subroutine calls, which are exchanging the contents of various registers. Or say SPHL, stack pointer is pointing to, is loading by the value HL register. Stack pointer is loaded by the value of the HL register pair. So these instructions may be required whenever you perform subroutine call and return. Now it may be necessary that, say, suppose you have performed one instruction execution, there may be another call of the same subroutine, say call address, same subroutine, before you have returned back. So in that case again it will go back to this point, and after the execution of this it will return here. So in this way you can have nested subroutine calls. However, the number of nesting that you can do will be decided by the size of stack. Size of stack will decide how many nested calls you can perform, because all the whenever you perform a subroutine call, the program counter values is stored in the stack. Each time you perform call in the nested form, it will be stored gradually in the stack one after the other. So stack will be uh, holding values, keep on holding values for each call, and and if the stack is limited in size, then at some point there will be stack overflow. So you have to keep track of that so that stack overflow does not occur, or you have enough size of stack so that nested subroutine calls can be performed to as many as possible. Now, after discussing the subroutine calls, uh, we have to discuss another type of conditional, another type of instructions. We have discussed those. Yeah, we have discussed unconditional jumps, conditional jumps, subroutine call and return. Now we are left with software interrupts. You are familiar with hardware interrupts. We have already discussed the interrupt structure of 8085. There we have seen there are 5 interrupts. One of them is non-maskable, trap, and RST 7.5, RST 6.5, RST 5.5, and INTR. These are maskable because you can mask them with the help of those flag bits. RST, there is a flag bit here, RST 7.5 flag bit here, here, and here, with the help of an instruction. Or you can disable the entire set of maskable interrupts by using disable interrupt instruction, or you can enable all of them by using enable interrupt instructions. We have already discussed this in detail earlier. These interrupts are known as hardware interrupts. These are known as hardware interrupts. And later on we shall see that these hardware interrupts are used for data transfer, interrupt driven data transfer. And trap, RST 7.5, etc. These are all hardware interrupts and commonly used for interrupt driven data transfer. Now there are another types of interrupts which are known as software interrupts. What is the function of software interrupts? Software interrupts are essentially instructions. For example, RST N is an instruction. That's why it is called software interrupt. You may be asking why it is called an interrupt. It is called an interrupt because whenever an interrupt or hardware interrupt occurs, the way the processor responds, the way the processor behaves, the same way the processor will behave whenever an instruction in the form of RSTN is executed, where that value of n lies in the range 0 to 7. So the code will be like this: a single byte instruction 1 1 n n n, where n n is this, and then 1 1 1 n n can have, let's say, three bits, so it can have 8 values 0 to 7. What it does, it stores the program counter value in the stack, just like whenever an interrupt occurs. And in that program counter low and program counter high is stored there. Then stack pointer is decremented by 2, and program counter with loaded by the value 8 into n. Suppose the value is 0, then 0000 is loaded into the program counter. If this value is 1001, then 80008 in hex is loaded into the program counter. So it depends what value will be loaded in the program counter by this. So in other words, you have got 8 software interrupts: RST0, RST1, RST2 to RST7. Say 8 software interrupts. And to execute each instruction, you will require number of cycles 3, and number of states required is 12. Why do you require 12? Because first instruction requires 6 cycles. That's why it requires 6 plus 3 plus 3. Now, where these are used, where these software interrupts are used? Whenever a software interrupt occurs, the processor status, that is program counter value, is stored in the stack. Then it jumps to a fixed location. That location is usually the address of a OS utility routine. This can be the address of a OS utility routine. For example, you have used PCs. In PCs, the BIOS routine, basic input output system, holds all the important input output routines, and that is in ROM, read only memory. And BIOS is implemented by using these software interrupts. All the BIOS routines are implemented by using these software interrupts. You may be asking that instead of using subroutine calls, why we are using software interrupts? What advantage it has got? We could have implemented all the operating system utility routines with the help of subroutine calls. Instead of that, why normally software interrupts are preferred? The reason for that is, you can see here that these software interrupts are faster than your subroutine calls. The subroutine calls, we have seen, they require quite long time. As you have seen, you require 18 clock cycles or 5 machine cycles. On the other hand, the software interrupts are requiring 3 machine cycles instead of 5. Number of states is 12 instead of 18. Moreover, their addresses are fixed, or you can say vectored. They use vector address. And that's why these utility routines can be ROM based. On the other hand, the subroutine calls do not have any vector address. Their address is provided as part of the instruction, call followed by address. So in a multi-user environment, at different instances of execution, those subroutines may be stored in different parts of the memory. In the first instance in some memory location, in the second instance in some other memory location, and so on. And as a result, a particular utility routine may be residing in different parts of memory at different points of time. So it is very difficult to use by a number of users. On the other hand, since they are ROM based, they are in stored fixed locations, many users can call them from the ROM, even in multi-user environment, and they can have only one copy. There is no need for multiple copies. So these are because of these advantages, the OS utility routines are implemented uh, by using these software interrupts. Another important use of software interrupts is implementing breakpoints. Later on, when we shall be discussing debugging, program debugging, you will see a technique known as breakpoint will be used. And breakpoints are nothing but in your program at some crucial points you want to insert a breakpoint. This is your breakpoint where you can insert an RST n instruction. So whenever RSTN occurs, it jumps to a utility routine with the help of which you can check whether up to this point the program has executed correctly or not, as desired or not. So this utility, this breakpoint is a very important tool for debugging a program. So software interrupts can be used to facilitate that. After discussing software interrupt, let us focus on another very important class of instructions, the status manipulation instructions. Before I discuss status manipulation instruction, let us try to understand what do we mean by status and what do we mean by manipulation of the status. We know that a microprocessor is nothing but a sequential circuit. In a sequential circuit, the output depends on the present input and the present state of the machine. What do you mean by present state? Inside the sequential circuit, there are several flip-flops which hold the status of the processor or which hold the status of the sequential circuit. So in this case also, some of these status are manipulated, are modified because of these status manipulation instructions. Now, obviously, whenever you execute a status manipulation instruction, there will be no data transfer, there will be no manipulation of data, there will be no change in the sequence of instruction execution. None of these will happen. So none of these actions which you have discussed in the context of data movement, data manipulation and program manipulation will take place, but the status of the processor will change. Let us see how it happens and what are the instructions. In this context, there are 4 such instructions: EI, enable interrupt, and whenever an enable interrupt is executed, which takes 1 cycles to execute, or 4 states or 4 clock cycles, 1 machine cycle and 4 clock cycles, the interrupt is enabled. What do you mean by that? You may recall that we have discussed in detail the interrupt structure of 8085, and there is a flip-flop, interrupt enable flip-flop. So by executing enable interrupt, this particular flip-flop is enabled or set to 1. Whenever it is 1, as you can see here, then these maskable interrupts are enabled. On the other hand, if you execute disable interrupt, and then this interrupt enable flip-flop is resetted. So it is connected, as you can see here, EI is connected to set input of this flip-flop and DI is connected to the reset input of this flip-flop. So by executing enable interrupt instruction, this flip-flop is set, and by executing disable interrupt instruction, this flip-flop is set. So we can say that by executing enable interrupt and by executing disable interrupt instructions, the flip-flop which is part of that interrupt structure is modified. What is the outcome of this? Whenever a flip-flop is modified, obviously nothing happens at this moment. However, subsequently, whenever an interrupt occurs, it may be accepted depending on which particular instruction has been executed. If enable interrupt is executed, then those interrupts will be enabled and they will be accepted. On the other hand, if disable interrupt is executed, subsequently no such no such interrupt will be accepted. That's why what is done in practice, you what you do, suppose you have written a interrupt service subroutine. Say this is your interrupt service subroutine, and it starts from here and it ends here. If you want that as you enter this interrupt service subroutine, the no interrupt should be accepted. So what you should do, immediately after jumping to this interrupt service subroutine, you should execute one disable interrupt instruction. So if you execute a disable interrupt instruction, no interrupt will be accepted after this instruction is executed. However, as you go out of this interrupt, returns to the main program, then you have to execute, of course this will be the return. Before that you should execute the enable interrupt instruction. So you see, because of this, the status of the microprocessor is changing. However, you are not modifying the you are not performing any other operation by using these instructions. Similarly, in case of these two instructions, CMC, complement carry, what you are doing here, there is a, you may recall that the register organization of the 8085, here there is a carry flag bit as part of the program status word. Normally this carry flag bit is modified as the outcome of an instruction execution. Whenever you perform addition, subtraction, then this carry flag bit is modified based on whether there is carry or not. However, by executing this instruction CMC complement carry, the carry flag bit is modified in this way. The complement of that bit is loaded into carry flag bit. So as a result of this carry flag bit gets modified, and subsequently some decision making can be done based on this flag bit. We have already discussed those conditional branch, conditional subroutine instructions. There we have seen that the outcome depends on the, can be the execution, the program can be written based on the value of that carry flag bit. That means the branch can take place based on this value, and that value is getting modified here. Similarly, this STC, that is your set carry. By using this set carry instructions, what you are doing, this carry flag bit is set to 1. Here also by you are modifying the carry flag bit, but you are not performing any other operation. So in all these cases, as you can see, you require 1 machine cycle and 4 states. So these 4 belong to the status manipulation instructions. Now let us consider another very important class of instructions, that is your miscellaneous instructions. Whenever we are not able to categorize any instruction in any other group, say data manipulation, data transfer and like that, then we categorize that as miscellaneous instructions. Let us see what are the miscellaneous instructions present in 8085. The first instruction that we shall discuss under this category is halt. This is halt. It has the code of 1110 1111 0011. Here it takes 1 cycles to execute and requires 5 states of clock cycles. What is the purpose of this halt? Obviously, this halt, whenever this is executed, the processor is halted. No further execution of instruction takes place. Then why it is present? Actually, this is used, we can say that use of halt. Why, what for it is being done? One very important use of halt is to use it as the last instruction. You have seen that in your flowchart the last symbol that you use it end. What you normally do, this end operation is replaced by a halt instruction. Why it is necessary? Whenever this halt instruction is executed, any other code which is present after this halt instruction will not be fetched and executed. Normally, suppose you have written a program up to this, and after that there may be garbage. Obviously, you want that this garbage codes which are not really instructions should not be executed. So, to prevent execution of garbage code present after your program, you will put halt instruction at the end of your program. So, this serves the purpose of end symbol of your flowchart. So, that is why halt is always written after the end of the program. Another very important use of halt is process synchronization. Let us see how the process synchronization is done by using the halt instruction. Suppose you have one microprocessor executing a program, say processor 1 or process 1 executed on one processor. There is another process is being executed in another processor. So, this is process 2. What you want, after a particular point is reached by the processor 1, you want at this point to be synchronized with this process reaches this point. What you can do, you can put a halt here. So, after execution of instruction up to this point, this processor or process 1 will stop here, stop execution. As you can see here, you can go back to the state transition diagram. Whenever the microprocessor goes to the halt state because of the execution of halt instruction, then it remains in that state. However, it comes out of the halt state whenever there is a DMA request, that is the hold. However, after performing this DMA operation, performing the data transfer, as long as it remains in the hold, obviously the data transfer takes place, DMA mode of operation takes place. However, as it comes out of this hold, again it returns back to the halt state. That means from the halt state it can come out only when there is a valid interrupt. And as long as there is no valid interrupt, it remains in that halt state. And whenever there is a valid interrupt, it permanently comes out and starts executing the next instruction. So, that is why this halt is also called as wait for interrupt, wait for interrupt. Now, what you can do here, after reaching this point, this processor can generate an interrupt to this processor. So, whenever this processor 2 generates an interrupt and it goes to the processor 1, it comes out of the halt and it starts executing from this point. So, you are able to synchronize the operation of the two processes. That means after this point, this will start execution, this will also start execution. So, you are synchronizing the execution at these 2 points with the help of this halt instruction. Now, apart from halt, there is another important instruction, that is your no operation. This is your no operation. Obviously, no operation means essentially it does not perform any operation. It does not perform any data manipulation, data transfer, it does not do anything. Then what it does? Only thing it does, it it takes some time to execute that instruction requiring one machine cycle or 4 clock cycles. But what purpose it can perform or what purpose it can serve while executing a program? Let us see what are the use of no. Use of no operation. No operations can be used for performing debugging. How? Let us see. Suppose you have a program and you have found that this program is from here to here, this point to this point, let's assume. And while debugging, you have noticed that these two instructions or maybe a single instruction has to be removed from the program. If you try to remove these instructions from your program, then obviously this latter part of the instructions, this part of the instruction has to be moved. So you have to rewrite the entire part from this part to this part and then shift it to this part. However, this can be avoided just by replacing those instructions by NOP, no-op. So if you replace those unwanted instructions by NOP, then what will happen? The program will execute and as if there is nothing, no instruction is present here. So it will give correct result. Nevertheless, it will take little more time because of this execution of instructions. But while debugging, what is important is to generate a error-free code rather than taking longer time. That's why whenever you write a program in the beginning, intentionally you can put few no-op instructions at some key points. So suppose here key points, and subsequently whenever you debug it, suppose you have to insert few instructions here, then those instructions can be replaced by those no-op instructions can be replaced by inserting new instructions. So no-op plays a very important role while debugging a program. It can facilitate debugging. So you can write a program in such a way by making use of no-op such that while debugging it is very helpful. Another very important use of no-op is delay generation. As we have seen, the no-op is although it is not performing any operation, it is taking some time to execute. So whenever you have to generate small delay, you can put a no-op instruction there, and so a small delay will be generated when no-op is executed. So these are the two important use of no-op. One is debugging a program, another is delay generation. Let me consider two more important instructions, RIM and SIM. RIM stands for read interrupt mask, and SIM stands for set interrupt mask. What you do here, that this is the code of the RIM, and it also takes one cycles and one machine cycle and 4 clock cycles. What you do before execution of, whenever you execute a RIM instruction, then this value, some value will be transferred to the accumulator, and accumulator will contain this information, serial input data. So you can perform serial mode of data transfer with the help of this instruction. You can read some data coming on the serial port, and also you can read the status, and you can see whether there is any interrupt pending on 7.5, 6.5, 5.5 line, and also you can see the status of the interrupt enable and the various mask bits, 7.5, 6.5, 5.5, as you have seen here. These mask bit status you can read, and using set interrupt mask, you can set the mask bits and the content is shown here. Before you execute uh, same instruction, you have to load it. This should be in the accumulator. This code should be in the accumulator. And it is a dual purpose instruction. With the help of serial output enable, you can transfer some data on the output line, SOD line, and also you can set the mask bit by putting this bit here. That means whenever this bit is 1, mask set enable is 1, you can set this mask bit 7.5, 6.5, 5.5, and you can accordingly the various interrupts will be masked and so on. So SIM and RIM are dual purpose instructions with the help of which you are you can perform serial mode of data transfer. You can also perform setting the mask bits of RST 6.5, 5.5 and 6.5, and you can also see the status of it. So we have, with this we conclude the discussion on the instruction set. Now just like you can make a garland by picking up flowers from your garden, and you can stitch them together to form a colorful, aesthetically beautiful garland. In the same way, you can pick up instructions from the instruction set and write a program. And what kind of program? It should be efficient in terms of execution time and the memory requirement. In the next couple of lectures, we shall discuss about how you can write program by making use of these instructions, the vocabulary of the machine. Thank you.